Alright, kiddos, you have your correction papers, your tests all passed out when we're doing another, well wait, probably mostly another example. Let me finish writing the first line. And then we pass out your tests as you guys finish the example. For instance, first of all, our answer is supposed to be what size?
3 by 2.
Okay. Second of all, first row, first column, what's 0 get multiplied by?
2.
0 times 2 is 0, plus what's negative 1 get multiplied by?
4.
Negative 1 times 4 is negative 4, plus what's 2 get multiplied by?
1.
2 times 1 is 2. Right? So cross down, first row, first column, cross over, first row, second column. 0 gets multiplied by negative 1. 0 times negative 1, 0, plus. Negative 1 gets multiplied by second times second. Negative 5, which would be 5, plus 2 gets multiplied by third times third times 6. 2 times 6 is 12. If you guys have not yet finished that puppy up, if you need to write it the long way, please feel free and write it the long way, but then go ahead and simplify. I might not get all the tests out right this second. I'll get a few out. We'll keep going. I'll get a few out. We'll keep going. Alright, these are my A's, you bet. Caleb, I have someone's scrap paper that fell off, by the way. I'm not sure where it went. Cameron, Tyler, Lucas, Ashley, Alex, Ricky, Maddie Garcia. This is no calculator stapled to calculator. Okay. Nathan, Jane. Oh, it's getting done. Austin, Sam. Still in the A's. Justin. Yes, Sam. Justin, JJ, Jesse.
You're special. No, dude.
Alright, this is in no particular order. Those are all the A's this time, but still some other good grades. Here we go. David, Abby, Jason, Nadia. Nadia, Ayla, Lawrence, Elaine, Denise, Emily.
What? In the bottom line of the 62. I got 40.
Naomi, Mia, Maddie Fuller.
42. I thought it was 60.
48.
So it is.
Mason, sorry,
What? So the answer is 46. Oh, wait. Thing, Maddie, what do you get? Test back? Your name? Walk on her. Oh, this one question was 6.
Alright, kiddos, listen up really carefully. The entire test had 10 questions. Help me out. 100% test, 10 questions. How many points for each one work? 10 points. So if you got a -3 or a -6 or a -7, that means something. I kind of was able to make an argument for something being right, or maybe a lot of it was right. They were 10 points each, so you definitely got partial credit on your questions. I think the air is about to turn on. I checked it when I walked in. Hang in there. I know it's warm. So, a lot of you guys got partial credit on a lot of the problems. A few of you just guessed and didn't show work. What am I supposed to do with that? I can't give you credit. But actually, on a couple of you, I was able to still give you credit like, well, the shaded was above, even though it was above on every single answer choice. I'll give them a couple points. Okay, I tried. I tried really hard. But But if you have questions on your partial credit, on your grading, make sure you let me know. Corrections are due on Friday.
On Monday.
With the grades day on Monday. Sound good?
Monday.
Okay. Let's go ahead and finish up this matrix multiplication. See how you guys did. After we do row 1, what do we have to do? Go to row 2. So hopefully when you guys went to row 2, you saw that 6 times 2 was 12, 0 times 4 is 0, 3 times 1 is 3. You moved across, 6 times negative 1 is negative 6, 0 times anybody is 0, 3 times 6 is 18. Last row, 7 times 2 is 14. Negative 1 times 4 is negative 4, 8 times 1 is 8. Second column, 7 times negative 1 is negative 7, negative 1 times negative 5 is 5, 8 times 6 is 48. You could have double checked this in your calculator, by the way, because you can input an A, you can input a B, and you can multiply 8 times B on the home screen. Your final answer for the first row, first entry should have been negative. Second entry, 17. Second row, first entry, 15. Second row, second entry. What do you guys get?
12.
Keep it going.
18.
And then?
46.
Got it. Dun, 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 dun. Check my mental math. Thanks for letting me know. You guys double check my mental math, right? We're good? Alright.
I put it in my calculator.
A different answer. Did you double check each of your entries? Double check each of your entries. Sometimes it's so easy, like to put one little number like that. Hey kiddos, as we're waiting for Caleb to double check in his calculator, isn't there a second part to the example?
Yes.
What's the second part say?
Yeah.
Okay, find BA. Why?
Oh, what? You can't do it.
Why not?
Because it's a 3 by 2 but times
B would be a 3 by 2 times a 3 by 3. Do you guys agree with your classmates and say it's not possible?
you know,
Not possible. Now what does this mean then?
it's
If I
mathematics people, that's not the same thing. If you could have a matrices,
Tyler's asking, wait, isn't A B B A? And my response is no. Now with numbers, 2 times 3 is 3 times 2, but with matrices, here is listen. Remember how we did those properties yesterday and we're like, oh yeah, they all make sense. We like didn't even write them down, most of us, right? These were with addition and multiplication by a scalar. What did we not write down any properties for? Multiplication by a matrix. Here's one of the key properties that you guys need to realize. A times B with matrices is not necessarily B times A. There's only one special time A times B can equal B times A, and it's only when, actually, we're dealing with an identity or an inverse. Otherwise, we're sunk. It's going to always be different. Because if you think about it, the orientation will change. A times B does not equal B times A, except in very, 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 very special cases. Is that a little bit counterintuitive for all of our training in math? Yeah. This is only not true so far with matrices. Alright, let's keep going. How'd you guys do this one then, finding A squared? 941! Nope.
No. It's 8 times 8.
Yeah, it's 8 times 8. Think about with killing puppies, right? Remember how I warned you guys when you do this, not to do a shortcut? How do I tell you to do a problem like this? Ignoring this for just a second.
Just FOIL.
Yeah, I tell you to write it out, right? Because if you write it out, hopefully you realize, oh, that's right, I have to actually FOIL the sum. There are 4 pieces, not just 2. So, similar idea with A squared. Don't think about it as A squared. That gets confusing. Think about it as A times A. And some people are already saying, wait a minute, but is that possible? What's the order of A? 1 row, 3 elements, right? 1 by 3. What's the other A? Well, same thing. This one's not possible. When is it possible to square a matrix? We could find the square if we were to do something like find b squared. We could, it would be possible if b was a square matrix, like, I don't know, 1, 2, 3, -7, just cause. Why would it be possible all of a sudden now? Because when you go to multiply it again, yeah. 1, 2, 3, -7, now we're okay, it's a 2 by 2 with a 2 by 2. When squaring, they have to be the exact same, so you're only able to square with square matrices. And we would, of course, do our process of going across and going down, but we already practiced that today, so we're going to go ahead and just say, you know what, ... We're just trying to show when it's possible, when it's not. And once again, do not think of a shortcut because you guys aren't that familiar with matrices. You have to write it out. B squared is b times b, a squared is a times a. Oh my goodness, where's our error? So, matrix multiplication, we've already kind of seen it doesn't work quite the same way that normal multiplication works, in that b times a is not necessarily a times b is not necessarily b times a. However, does that mean that none of the properties that we're used to are true? No. Aren't these ones kind of normal? Haven't we seen ones like these before, the associative property of multiplication? Or the distributive property? But here's something that we have to keep in mind. If we're distributing, we have to make sure if A is on the left in the beginning, A is on the left at the end. If C is on the right at the beginning, C better be on the right at the end. Because those matrix multiplications aren't able to go back and forth. Because matrix multiplication is not commutative, we cannot switch the order. If we switch the order, then we're in trouble. So as long as you see these properties and say, oh, hey, yeah, they make sense. And if you have not yet written them down or written it down, even though a lot of properties do make sense, please, 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 somewhere in your notes make a note that A times B is not B times A. Which means these cannot be switched and still be right. These cannot be switched and still be right. That would all be illegal. That would all break down. Okay, now, these are not ones to necessarily memorize. It's more of an understanding to have. Out of this entire page, what I need you to have written down somewhere, somewhere starred, highlighted, is only the following. And if you want to, you could go ahead and write down that quick little, make sure if you are trying to find a squared or b squared or c squared that you do a times a, writing it out. Kiddos in the back, that's a great thing to save at the very end of class next time, okay? Alright, let's keep going. What's so special about this guy called the identity matrix? He has a spiffy name, there must be something, right? It is the multiplicative identity, which means it's kind of like times 1 for numbers. 5 times 1 is 5, even though Algebra 1 kids have been struggling with that the last couple of days. I don't know why. 5 times 1 is 5. 1 times 3 is 3. It's the 1 is the multiplicative identity of numbers. For matrices, we've already seen multiplication is a lot different. So a 1 matrix would not be the multiplicative identity. Instead, the identity matrix would be. The identity matrix would be. And the property, I think, at the front or at the top is kind of what I wrote down below, so that's kind of silly. I'm just going to go ahead and write down, has the property of the additive, no. Multiplicative. I apologize. The additive identity is the 0 matrix. The multiplicative identity is the identity matrix. And here's why. We're going to practice cross down one more time. If we were to multiply the first row by the first column, pairing up the first with the first, the second with the second, the third with the third, you guys notice multiplication? 3 would be times 1, so 3 would stay. But 2 times 0 and 5 times 0, isn't that just plus 0 plus 0? So the only thing that remains would be the 3. If I cross down, cross over down, and go to the next row column, 3 times 0 is 0. 2, negative 2 times 1 is going to be negative 2. 5 times 0 is 0. So only the negative 2 stays. Now guys, if we continue the procedure, going down, going across, if you notice, it's going to end up being the exact same thing that it already is. With 3, negative 2, 5, 1, 0, 4, negative 1, 2, negative 3. That 4 is messy, I apologize. So the nice thing is at this point, once you've seen it kind of once, you can say, oh sweet, anytime a matrix is times the identity, I'll just leave it the same. And the cool thing about the identity is it doesn't just work one way. It doesn't just work, a matrix times the identity is itself. It actually also works the other way, and if we were to go ahead and solve it out, if we were to do the first times the first, and the second times the second, and the third times the third, we would see yet again, no matter which way you multiply it, you still end up with the non-identity matrix involved in the multiplication. So this is one of those special moments where if B equals I, A times B will equal B times A, but only if the second matrix is the identity matrix. Only with the identity matrix so far that we have seen can you multiply both ways and have it work out the same. However, do you guys notice the orders? What's the order of the original matrix? Ooh, it's a square matrix. It's a 3 by 3. And what's the order of the identity matrix? So we're still just dealing with square matrices. If it was non-square, well, we'll talk more about inverses, I think, next section. But if it's non-square, there's a problem. Basically, there is no possible inverse. Now, 2 quick applications of inverses. Now let me zoom in. Actually, my thing is tilted weird. There we go, that's better. 2 quick applications of matrices. First of all, matrix multiplication can actually be used to show systems of linear equations. Systems of equations, remember how we talked about how matrices can help solve section 8.1, we were RRE-ing row reduced echelon form, using row operations to simplify. But that was with an augmented matrix. We can actually use matrix multiplication to help us realize why we orient equations the way we do, in the sense of we can pull out from matrix multiplication. It's like we're factoring out those variables, which this one has x1, x2, x3, but it could be x and y and z. But the dealio is, if we pull those out, and technically if you think about it, if there was multiplication that happened, this would have been in the first spot, this would have been in the second spot, this would have been in the third spot. And if you notice, that's the exact same orientation of all the rows. There we go. We can pull out all of those variables into one single matrix, which we would call the variable matrix, or X. So we're kind of seeing after the fact some of the theory behind why we were able to do our row reduced echelon form. But it's all about orientation. It's all about keeping everything even. Praise the Lord, I think that's finally there. And so just to label things just a little bit, even though I've used these names, I don't think we've written these names. A is called the coefficient matrix. It's all the coefficients of all the variables. It only works if you have them oriented correctly because of this factoring, undoing the matrix multiplication dealio. This one is called the variable matrix. And this last one is called the constant matrix. If we coefficient matrix, variable matrix. Actually, probably don't need to make that coefficient plural. Let me just make it singular, coefficient. Coefficient matrix, variable matrix, constant matrix. And this is getting us ready for next section where we're going to see, hey, there's another way to solve matrix equations without having to do reduced echelon form. And it basically has to do with the question, hey, whenever we have an equation like this with numbers times variables equals numbers, don't we just want to divide? The answer is yes, but in matrices or with matrices, division doesn't work. We don't do division with matrices. So instead, to solve this equation, since we can't divide by a, what we're going to learn to do, next section, don't worry, not this section. We're going to learn that the only way to undo a is to multiply him by his inverse. If we multiply him by the inverse on the left, we have to multiply on the left the inverse by the other matrix as well. So we're going to see this next section as a quick little intro to say, hey, this is coming. If we're given an equation with matrices, we still want to undo, we still do operations to both sides of the equations. What we do to one, we do to the other, but there is no such thing as matrix division. Instead, we use inverse matrices. And so we'll learn all about inverse matrices in section 8 point whatever. 8 point, where are we at now? In 8.3, which we were supposed to start today, but with our nice drill, that's not going to happen. But that's all right. At least we'll finish 8.2. We're going to finish the drill. We're going to finish the section with one word problem. You don't see a lot of word. Oh, there we go. You don't see a lot of word problems with matrices, to be honest. You only see a few. But it gets kind of confusing when you do. So let's start off with the first part. Typo, that's awkward. At a local dairy mart. At a local dairy mart, the numbers of gallons of skim milk, 2% milk, and whole milk sold over the weekend are represented by A. Huh?
Are those like days?
Yeah, how do you read that? They're just lots of numbers. Well, what are the two labels in the information so far?
Days and
Types of
milk.
Milk.
Number of milks.
So we have milks. That's really bold. Different types of milk. And we have days of the weekend. Wait a minute, hold
I
on.
don't even know which one.
Why is this a 3x3? Doesn't the weekend only have 2 days?
Yeah. Friday.
In businesses, Friday definitely still counts as the weekend, right? So we have milk and we have day. We have the different day and we have the different types of milk. Probably make that plural. But we don't know who's who. So let's keep reading and see if we can figure out who's who from the next piece of information. The selling prices in dollars per gallon and the profits. Okay, so selling. Now we have 2 new quantities, right? The selling prices in dollars per gallon and the profits in dollars per gallon for the 3 types of milk sold by the dairy mart are represented by B. Wait, so hold on. How can we label B? Because he has two quantities for columns, 3 quantities for rows. Can we figure out which one goes where for B and then maybe have it help us for A? Okay, so where would the milk go?
For the rows.
For the rows, how come? How many different types of milk do we have?
3.
Okay, so we must have skim, 2%, and whole. So if the milk labels the 3 rows, then question, what are the labels for the columns?
Selling price.
Why? Can we tell just logically selling price must come first and profit must come second?
Because you sell it for more than.
Yeah, you sell it for more than you make. Right? So to actually pay your costs. Selling price involves costs and profit. Okay, what's letter A say to do? Why are we multiplying A times B? Well, hold on. Don't we have to go across A and then down B? question. In order for this all to match up, where would milk go in the original? Exactly. If we need this all to match up, first with first, second with second, third with third, milk must be the columns. So what does that mean that the rows are? So we can say Friday, Saturday, Sunday. Now can we talk about the order real fast? What's the order of the original? Now guys, this is definitely a calculator problem. Don't stress. It's a calculator problem. We're just trying to see if we can understand how to interpret the data. What does the 3 rows, or what are the 3 rows measured in or measured by? The first 3 in the order of the first matrix. What are the 3 rows measured by?
Days.
Does that make sense? So we have days here. And then what would the columns be?
No.
So question. First of all, do these match? Yes. What order is our answer going to have? But what units or what labels is it going to have? Is it going to have for what day, what money we made? Does that make sense?
Yeah.
So if we use what we know about matrices, the insides match because they're both milk, well then the outsides, sorry, I tilted it, are going to be days and money. Now kiddos, that would definitely be a calculator problem, but I wanted to help you guys realize how we can interpret matrices and data given in matrices. You're right, we're not finishing this example. You guys are going to be totally frustrated that you're all packing up. Homework is due. I think that's the same homework. The homework number might be different though. What are we on, 49? I would double check online, but this very well may be the exact same assignment. I used to write things a little differently at the end of notes. And that is what's due tomorrow. Alright, cool kids, come tomorrow, ready for us to bust out. Wait. Why didn't the bell ring?
I don't know, bro.
It's 45 though. Hi guys, what's going on? Maybe that's good drill.
You have a pep rally tomorrow, right?
Yeah, not today though. All that I know.
I haven't gotten 100% since like 5th grade.
5th grade?
I don't know.
Something like that.
I never really remember. I mean, it's managed, yeah.